A shipwreck can look motionless, but salvage begins with a cruel fact. The water is often helping to hold the wreck together. Goods that support too quickly and weakened timber or torn steel can collapse under its own weight. We are here to determine the GOAT of recovery of large shipwrecks as single structures. The field is recovery of large shipwrecks as single structures, so the hardest recoveries are not simple lifts. Inders must understand the seabed, the structure, trapped water, suction in the mud, changing weather, and every path through which force will enter a hull that was never designed to be handled this way. Sometimes the answer is a cradle, sometimes it is a forest of cables, sometimes it is parbuckling, which means rolling a capsized vessel upright through controlled rotational force rather than trying to hoist it vertically. This field is narrower than ordinary wreck removal. The contenders must recover a substantial ship hull as one structure, not merely retrieve cargo, cut up debris underwater, or raise a few historically valuable objects. The comparison turns on 5 things: the size and condition of the wreck, the difficulty of controlling it, the human and environmental hazards, how completely the mission achieved its purpose, and what later engineers learned from it. Preservation also means different things. An archaeological ship may need decades of chemical treatment after it reaches air. A military wreck may be raised for remains, evidence, or strategic material. A polluted wreck may simply need to leave without poisoning its surroundings. That is why the greatest operation is not automatically the deepest lift or the heaviest hull. It is the campaign that controls the most difficult chain of failures from seabed to final destination, without losing the wreck halfway through. Vasa had spent more than 3 centuries in Stockholm Harbor when a modern salvage campaign finally committed to raising the 17th century warship. Divers excavated tunnels beneath the hull so cables could be passed under it and connected to lifting pontoons. The team did not drag the ship straight to the surface. It moved Vasa through a sequence of cautious underwater lifts, shifting the hull into shallower water before the final raising in 1961. That staged approach reduced the consequences of a single bad movement. Reaching air only changed the problem. Waterlogged wood can shrink, crack, and lose its shape as it dries. So conservators replaced water inside the timber with polyethylene glycol, a water-soluble synthetic wax. Spraying continued for 17 years, followed by 9 years of slow drying. Vasa transformed the conservation of large waterlogged structures and remains astonishingly complete. Yet its sheltered harbor, relatively controlled lift path, and modest scale, compared with later steel wrecks, keep it from dominating the whole field. The Mary Rose presented a different kind of fragility. Much of the Tudor warship had disappeared, leaving a surviving starboard section that had to be supported, without pretending it, was still a complete self-bracing hull. Inders placed a purpose-built tubular lifting frame above the wreck. Wires connected that frame to bolts positioned through major structural beams, while hydraulic jacks raised the hull just enough to break the suction of the seabed. The suspended hull was transferred into a bespoke steel cradle nearby. On the 11th of October 1982, the crane barge lifted cradle and ship together, turning an exposed archaeological structure into a load that could survive the journey ashore. Its conservation then lasted for decades. Polyethylene glycol spraying ran from 1994 to 2013, followed by years of carefully controlled drying and continuing humidity monitoring. Few salvage projects have treated arrival at the surface as merely the midpoint so honestly. The Mary Rose recovery was exquisitely sensitive and scientifically productive, but it raised the largest surviving portion, not an intact ship, from a relatively accessible site. It wins on delicacy more than on total physical control. At Pearl Harbor, the United States ship Oklahoma demanded violence in slow motion. Torpedo damage had capsized the battleship, leaving it on its side in shallow water. The task was to rotate a badly damaged warship without letting it slide or break apart uncontrollably. Inders built 21 electric winches along Ford Island and ran miles of wire through blocks, pulleys, towers, and attachment points on the hull. Instead of one heroic pull, the system spread force across a carefully managed network. As the cables tightened, Oklahoma rotated in stages. Photographs show a ship slowly returning through impossible angles, while the salvage team adjusted the geometry and reinforced the structure around it. Writing was not enough. Workers sealed openings, pumped compartments, and eventually refloated the hull in November 1943. By late December, it had entered dry dock, a complete sequence from capsized obstruction to movable ship. But Oklahoma never returned to service. The objective was recovery of remains and useful material, not preservation of the vessel as a functioning or cultural whole. Its parbuckling was monumental, yet the ship itself remained beyond rescue. Kursk moved the contest into deep, hostile water. The Russian nuclear submarine lay 108 meters down in the Barents Sea after explosions killed all 118 crew members. The prepared section for the main lift weighed about 9,000 tons. The hazards were exceptional: damaged structure, possible unexploded weapons, 2 nuclear reactors, missiles, cold water, and a narrow seasonal weather window. Before lifting, the unstable bow had to be cut away with a specialized saw wire operated from seabed anchors. Divers cut 26 openings into the pressure hull for lifting connections. The modified barge Giant 4 then raised the submarine beneath itself, turning vessel, and barge into one transport unit for the journey to dry dock in Murmansk. Kursk is the strongest rival because depth, nuclear risk, structural uncertainty, and human consequence were combined in one lift. Its limitation is equally clear. The ruined bow was deliberately separated, so the mission recovered most of the submarine rather than controlling the entire wreck through every phase. The Costa Concordia wreck removal project is the GOAT of recovering large shipwrecks as single structures. It did not win because the original disaster was admirable. It wins because the response had to control a damaged floating city through an unprecedented sequence of engineering problems. The liner rested on its side beside Giglio Island, supported unevenly near deeper water. The site combined a deformed hull, a steep underwater slope, a busy coastal community, and a sensitive marine environment. Losing control could have sent the wreck farther down or released more contamination. SUD made every decision unforgiving. The ship was about 290 meters long. Its steel structure alone weighed roughly 56,000 tons. The chosen plan required removing it as one unit, rather than dismantling thousands of cabins and public spaces on site. First came restraint. Enders stabilized the wreck and mapped its damage so forces could be applied without starting an uncontrolled slide. Multiple measurement systems watched the ship continuously, because a movement measured in centimeters could change the entire recovery geometry. Then they built a destination for the ship before moving it. 6 underwater steel platforms, supported on the granite slope and backed by an artificial seabed, can the ledge on which the hull could safely land after rotation. Large steel caissons, also called spunsons, were welded to the exposed side. Some would add controlled weight during righting. Later caissons on both sides would provide buoyancy for refloating. The same boxes had to serve different jobs at different moments. The pulling system used cables and strand jacks, mounted on retaining structures. A strand jack grips bundles of steel strands and advances them in controlled steps, allowing enormous loads to move slowly enough for engineers to measure, pause, and correct. On the 16th of September 2013, the parbuckling began. The cables first freed the hull from the rock and started the rotation. This was the dangerous threshold. Before the ship moved, nobody could be certain how badly its hidden side had deformed. As the wreck turned, seawater entered the port side caissons. Their growing weight helped continue the roll, gradually shifting the work from strand jacks to gravity. The operation did not defeat gravity. It arranged the geometry so gravity changed sides. After roughly 19 hours, the ship stood upright on the new underwater support. The result exposed crushing damage on the side that had rested against the rocks, but the hull had completed the rotation without escaping the controlled path. That spectacular moment was still not a recovery. The newly exposed side needed repairs and additional caissons. Enders had to transform a wreck sitting on an artificial ledge into a stable floating object, while accounting for water, debris, and damaged internal spaces. Eventually, around 30 caissons were attached. By pumping water from them in a controlled sequence, the team increased buoyancy and lifted the hull from its support. Refloating was less theatrical than parbuckling, but it depended on every earlier phase having preserved enough structural control. In July 2014, the wreck left Giglio for Genoa. The journey covered about 280 kilometers over 5 days, with a convoy of 14 vessels and more than 500 people involved. A ship that had been fixed to rock was finally mobile again. Kursk still wins the argument for depth and concentrated hazard. But this project controlled a far larger and more asymmetrical wreck through stabilization, foundation building, rotation, repair, refloating, towing, and environmental cleanup. No single lift could solve it. The limitation matters. The liner was not restored, it was dismantled. The operation was long, extraordinarily expensive, and born from a preventable catastrophe that took lives. Injuring success does not redeem the disaster. It only explains why the removal deserves study. Its GOAT status matters because it shows what mature salvage really is. Not one giant machine, but a disciplined sequence in which every temporary support prepares the next move. The greatest recovery made gravity, buoyancy, steel, and the sea cooperate, one controlled failure at a time.